very last thing in physics 20 is Doppler effect. Okay, so we'll go over that today. Tomorrow we'll do our unit exam review. Okay, Wednesday we'll start our final exam review. Thursday's your unit exam. Okay, Friday we'll go over the unit exam. I'll answer a few more questions for the final. Okay, and then next week is all your questions and answers. So please make sure you've started some of your exam prep so you can make the most of those days. Okay, otherwise it's going to be kind of me talking about things I've already talked about, right? Which maybe doesn't help you as much as if you had specific questions. So make sure you come with specific questions. Okay. All right, so we got to go over what the Doppler effect is, how the Doppler effect changes the pitch of a sound. Now, the way that sentence is stated is a little bit misleading / wrong, right? Pitch is associated with what property of a wave, excuse me. The pitch of a sound wave has to do with its frequency. Now, we've already been told frequency can't change. You can't change the frequency of a wave once it's been produced, right? But what we can do is change our perception of it due to either the movement of the observer, that would be us hearing the sound, or the source, whatever it is making the sound, right? If either of those two things is moving, then what it does is because they're moving and producing waves at the same time, it actually stretches or compresses the waves more than they're actually being, more than their actual wavelength, right? So it's not that the frequency is actually being altered, it's just because two things are moving, one or two things are moving, that we perceive it to be different, even though it's not, all right? All right, so the Doppler effect is responsible for the sound barrier as well. We'll talk about that. But first, we're going to have Sheldon Cooper explain to us what the Doppler effect is. How many people have seen the Halloween one? Okay. Okay, so Doppler effect, okay, like Sheldon said, is the perceived change in the frequency of something. It's not an actual change because we know the frequency of a wave can't change once it's produced, right? But the Doppler effect can cause us to hear something that's slightly different. You've probably experienced this if you've had like, let's say like a fire truck or an ambulance approaching you, okay, and then pass you and go away. Does it sound different on either side? Right? Most things do. Most things sound different when they're coming towards you than when they're going away, and that's the Doppler effect. Okay, that's the fact that because the car is moving and producing sound, okay, whatever it is, the ambulance, whatever, okay, the sound waves don't get as far away from it as they should because it's moving as it produces them, so they don't run away as far or as fast as they would if it was stationary. So when it's approaching you, you hear a higher frequency or higher pitch of sound. When it's going away, you hear a lower pitch because now, as it produces the waves, it actually runs away from the waves and stretches them out, or appears to stretch them out, because the next time it produces a wave, it's actually further away than it should be. And so as a result, you hear a lower frequency of sound as the object goes past you. All right, everybody okay with that idea? All right, I've got a couple of examples here. Because when something is moving and it's producing waves, because the waves in front of it essentially don't get as far away, if you're going close to the speed of those waves start to pile up in front of you. All right, so if you're in an airplane and you're going close to the speed of sound, all right, what starts to happen is instead of these waves being kind of far apart like they are here, they start to bunch up because as you produce them, they can't run away from you. You're going almost as fast as they are. And as you approach the speed of sound and now you're going the same speed they are, they can't get away. So the waves you produce pile up in front of the aircraft. Now, how do you make sound waves? Sound waves are a series of compressions and rarefactions. So essentially what you have in front of you now is a wall of extremely dense compressed air. Right? Because you're in an aircraft that's going the speed of sound, that's going to be loud. Okay, jet engines are very, very loud, and as a result, okay, all of that loud, all of that sound, okay, all of those compressions now pile up in front of the aircraft, which makes it very, very difficult for the aircraft to accelerate until it can punch through. This was a big problem in the early stages of the space race, okay, back in like the late 40s, okay, when they were trying to build something that would go fast enough that we could get it into orbit and out into outer space. Well, the first challenge to that was it had to go faster than the speed of sound, and that was a big problem. because for years, both the Russians and the Americans had been trying to build an aircraft that could break the sound barrier. Okay, they called it the sound barrier because every plane they built that could go as fast as sound just blew up when it went as fast as sound. Right, and when they watched them closely, it looked like they ran into an invisible wall in the sky, which is essentially what they did. Okay, the pilots would report that their plane would start to shake, and no matter how much throttle they gave, okay, the plane could not accelerate further, and eventually the plane would shake to the point where it would just blow up. It would fall apart, and then the fuel would ignite, and it would blow up. Right. So what they were trying to do is just, well, maybe we're just not building powerful enough planes. It was a very this may be a little bit sexist, but a very manly way to go about solving a problem. We just put more power in. Okay, we just make it more powerful and that'll solve the problem. So essentially what they started doing was dropping rocket-powered planes out of the bottom of bombers. Okay, and so they went through a lot of test pilots. It was during the late 40s was a bad time to be a test pilot. Okay, because you basically just got to sit in this plane and this bomber would carry you up to whatever altitude, very high, so it would be cold and the speed of sound would be lower. Okay, and then they would just, well, they called it light the candle. They would light the rocket engine and drop you out of the bottom of the bomber, and then away you go and smash into the sound barrier you went. It wasn't until they started really kind of figuring out why the planes would start to shake, that there was this increased air resistance, that they started to develop a different shape to the nose cone, right? If you look on like older fighter aircraft, the nose cone comes into a point and then there's like this needle. It almost looks like a spear that comes off the front, okay? That's actually there to help disrupt the extremely dense air and create essentially a low pressure area or vortex through which the plane can pass, right? You'll notice that most passenger aircraft don't have that shape to their nose, unless it's the Concorde, which doesn't fly anymore because it was a death trap. But okay, it was a supersonic passenger aircraft. The problem was it was really hard to land because it had to have its wings a certain shape and because it had to have that nose. That nose is fine on a small aircraft. On a larger aircraft, the Concorde's nose actually changed its angle depending on whether it was going to go supersonic or whether it was going to land. It would the nose would go down. Okay, in order to land. It was, yeah. It only flew to two places, London to New York. It was not, or Paris to New York, something like that. Anyway, it was not a very useful plane, other than it could go fast. So there's issues with going faster than the sound barrier. Once we figured those out, okay, the first guy to break the sound barrier, okay, he became the fastest man in the world by a factor of 2. Okay, because he passed through the sound barrier. There was this massive boom that everybody on the ground heard and just assumed he was dead. Okay, and they were, well, back to the drawing board. That didn't work. And then he comes over the radio and he's saying to them, there's something wrong with my Mach meter. That's the speedo. Okay, it's just jumped plumb off the scale because he'd gone through this thing that was holding everybody back. And suddenly he was in this rocket-powered aircraft that was going really, really fast. Okay, because now the resistance of all that compressed air was gone. Okay, and that rocket engine just shot him up to like past Mach 2. They actually told him, like, throttle back. We need you to land that thing because we got to figure out what we did right. Okay, that was their trial and error approach. Yeah, breaking through the sound barrier is actually the most kind of fuel or energy intensive part, is getting through that wall. Now, the way we design planes makes it actually look pretty easy anymore. But yeah, back in the day, it was, you know, they would just rock and shake and whatever. Now there's kind of a gentle bump and boom, they're through. Okay. All right, it actually looks pretty cool if you ever see a plane do it. Okay, there's actually 2 different booms. There's one when the nose passes through the sound barrier and one when the tail, because they're a different shape. Okay. But you can actually see as well that it makes this cloud that's only there for an instant and then it's gone. Because right there, all of that water vapor that's in that air is compressed rapidly, okay, to a point. Now, if you've taken chemistry, you got like the Boyle's law, Charles' law, and the ideal gas law, okay, and they all tell you about what happens when you put a gas under pressure, you can turn it back into a liquid. Okay, well, that's what happens here. Okay, all the water vapor that's in that air gets compressed so heavily that it actually condenses quickly, forms this cloud, and then when the pressure is released, poof, it's gone. Okay, that stuff just goes back into a vaporous state and you don't see it anymore. All right? Yeah. Everyone all right with how the sound barrier works?
When you go to slow down, is there any problem?
No, you pass back through, but it's not as big a deal to pass back through as it is to initially punch through. Yeah. All right, your sound is more catching up with you as opposed to piled up in front of you. All right, I'll show you a quick video here of that, and then we'll move on. So with the sonic boom, there was a lot when they first were able to break the sound barrier and realize there was this massive overpressure that got released very quickly. Okay, thoughts automatically turned to, okay, that seems like a lot of energy. That could that be destructive? Could we use that as a weapon? The thought being that if they flew low enough over the ground, like if there were a bunch of troops on the ground, that the massive overpressure would throw them out of the way and like pull them out of the only problem with that is you're flying really low to the ground and people can shoot at you. So yeah, you mean you're going fast, but still, people can shoot at you when you're that low. The other problem was it didn't work, right? Like she said, in that cone, the pressure is not that much greater than normal atmospheric pressure. Yes, there's this massive overpressure right at the nose, but it dissipates so quickly that it can't even all it can really do is like rattle windows and stuff. Okay, MythBusters actually did a thing on this one season where they flew an F-18 as low as they were like allowed to go over top of this like dummy house they had built, and they couldn't even break the windows. Okay, like the thing was only like 100 feet off the ground, and it was going right at this. It broke the sound barrier right over top of that house and shook the windows. That was it. Okay, couldn't break the windows, couldn't like knock the china off the shelves inside. Okay, it just wasn't practical. Okay, unless you were right on top, which is dangerous for the pilot. Okay, again, exposes them to small arms fire from the ground. So it didn't really work in terms of that. Okay, so if we're looking at situations where we hear or perceive the Doppler effect, it has mostly to do with sound, right? We don't have anything that moves really fast for us to perceive any change in frequency of light, okay? When a car is coming towards you, its headlights don't look bluer than normal, okay? Like unless it was going near the speed of light, we wouldn't really notice any Doppler shift, okay, for a vehicle or anything like that. To do with light, to do with sound, yes, because sound travels a lot slower, right? So we can definitely perceive that. So when the plane is when the train is stationary, right, we see that on either side of the train, the waves are the same. Okay, the wavelength of the waves here and the wavelength of the waves here, thus the frequency on both sides is the same. But once we put the train in motion, as it produces sound, the sound doesn't get as far away before the next wave is produced. And so as a result, the waves start to bunch up. And anyone in front of the train hears a higher pitch. Anyone behind the train hears a lower pitch. Everybody all right with that? Okay, so that's like a visual representation of what we heard in those two videos with the car horn and the siren. Okay, the same is true for light, but again, we can't perceive that. Okay, our eyes just don't have the ability to perceive that. However, we do have instruments that can detect this Doppler shift, and it's what we use, okay, to determine things like whether the universe is expanding or not. Okay, we know that the universe is expanding because when we look at very distant objects in the sky, they are shifted towards the red. Okay, that is the wavelength of light they produce is a little more red than it should be, right? Not something we could see, but it's something that like X-ray telescopes and things like that can observe, and that must mean that they are moving away, and thus the universe is expanding. Okay, things like that. It also helps us to determine things like how far from other stars, exoplanets might be, things like that. We can determine the Doppler shift of those things as they're moving around. Okay. So we have the bunching up in front, producing the higher pitch. We have the expansion in the back. It's not really changing the speed of sound. The train's sound is still the same as it is when it's stationary. We just don't perceive it to be that way because of the movement of the train. The same could be true if you were running towards a stationary sound source. Okay, so if I had a source that was stationary and I was running really fast towards it, the Doppler shift would be there because it's producing sounds, but I'm moving through the waves faster than I would if I was standing still. So I would perceive a Doppler shift in that way as well. Everybody kind of follow on that? Okay, so if you had like a fire truck on the side of the road and you drove past it, it was stationary and you drove past it, it would be exactly the same as if it drove by you. All right, so either the source or the observer can cause the Doppler shift. Right? In Physics 20, you are only ever asked to do problems where the source is moving. Okay? We used to have to do ones where both the source and the observer could be moving, but now they changed the curriculum. I don't know why, it wasn't any harder, but okay, now you only have to do problems where the source of the sound is in motion. Okay, so we've talked about that already. We can skip over that part. Okay, so we're going to look at some examples here real quick. Sheet. Okay. On your formula sheet, it actually has this up top as well. Okay, that's the formula for the Doppler effect. Okay, the top part of this has to do with a moving observer. So you can alter your formula sheet right now so that it just looks like that. You won't have to do any problems with a moving observer. Okay, just with a moving source. All right, so to kind of lay out what the parts of the formula are here. This F with nothing beside it is the Doppler frequency. Okay, and that's the one you hear. Okay, so it's the observed frequency. F0 is the original frequency. Okay, V is the speed of the waves. So in most cases, that'll be the speed of sound. And Vs is the speed of the source. Okay, just so you know what each part of that formula stands for. Why is there a plus minus in this formula? Right, it's different whether it's coming towards you or moving away from you. Okay, in one of those situations, you'll need to add the speed of the source. In another one of those situations, you'll need to subtract the speed of the source. So now let's figure out which one is going to require which. Okay, so in a situation where the source is moving towards us, well, can't write very well this morning, towards, okay, F is what compared to the original? If the source is moving towards me, what do I hear? Right, I hear a greater frequency. Okay, so that means this F is bigger than F0, right? If the object is moving towards me. So am I going to want to add or subtract if I want F to be greater? Keeping in mind, for F to be greater, whatever this bracket comes out to needs to be greater than what? If multiplying F0 by that number is going to make F bigger, then what's in brackets has to be greater than what number? Than 1. Okay? Whatever's in brackets has got to be greater than 1. So that means then that the top needs to be bigger than the bottom. Everybody follow there? Okay? If I want what's in brackets to come out to be greater than 1, the top's got to be greater than the bottom. So am I going to add or subtract? I'm going to subtract. Okay? So if I'm moving towards, I subtract. Okay? If it's retreating or moving away, then I add, because then that'll give me a decimal in brackets, and when I multiply, okay, by that decimal, then F will be smaller than F0. Okay? Manipulation of this formula can be a little bit tricky. All right? So we're going to kind of walk through how we manipulate this, okay, for each of the things we'll have to solve for. Okay? One of the other things you need to know is that you will not be asked to solve for V. Okay? You'll be asked to solve for Vs. You'll be asked to solve for F or F0. Okay? But never V, because we can't guarantee that you've taken Math 20 yet, and as a result, okay, you wouldn't know how to do that whole, the F word factoring. Yeah. Okay. We can't guarantee that you know how to do that yet. Okay. So you never have to solve for V. Okay. In this situation. All right. So let's solve for the three things that we have to solve for here. Okay. So here's the formula: F equals F0. Okay. Times V over, and let's say that we have an approaching object, so minus Vs. All right. If I want to solve for F0, what do I do? No, that'll solve for 1 over f0. f0. Right, I just bring the whole thing in brackets over to this side, right? It's in brackets, I would do it first anyway, okay? So if I'm solving for f0, it's just gonna be f divided by v over v minus vs. I just bring the whole bracket over, right? I'm multiplying by what's in brackets, I just divide the whole bracket over, okay? All right, so that's how to solve for f0, okay? What if I wanna solve for vs? What should I move first? I should move f0 first, yeah, because that'll help me get rid of the brackets. All right, so I'm going to divide both sides by f0. All right, vs is on the bottom. If I want to solve for something, I want it to be on the top. Agreed? All right. Rules of algebra are move what's not attached first, do what I do to one side to the other, and so all the easy stuff, right? Okay. As long as I do to one side what I do to the other, I can do whatever I want in algebra. So what I'm going to do is I'm going to flip both sides, okay, so that vs ends up on the top. So I'll have f0 over f is v minus vs over v. All right, what do I do with this? I want to get vs by itself. What do I do with this v on the bottom? Times it, right? I'm dividing by it, so I multiply both sides by v. Okay, so now I've got FOV over f equals v minus vs. Now, if I just move the other v, I'm solving for negative vs, which is fine as long as you remember you're solving for a negative number. I don't like that myself. Okay, so what I'm going to do is I'm going to add vs to both sides, and then I'm just going to subtract this over. Okay, so I'm going to go v minus FOV over f. Okay, that'll solve for vs. Okay, that's if the object is approaching. Okay, if it's retreating, okay, then I'm already adding. I just subtract v over to the other side. All right, so a little bit of trickier algebra. You haven't had any tricky algebra in this unit at all, so okay, that's your little tiny bit of tricky algebra for this unit. Okay, let's have a look at this example problem here. Okay, so I have a train traveling at 30 meters per second. What did they just give me there? Vs, that's the speed of the source. Okay, so 30. Okay, its whistle generates a sound wave with a frequency of 224 hertz. Okay, is that the sound I hear or the original actual frequency? That's the original actual frequency, okay? It says it's producing this, that's the FO. That is probably the most common mistake when doing these. It isn't the algebra that nails people on these, it is mixing up the frequencies. Right, this is the original frequency. You are standing beside the tracks as the train passes. Key, you are standing beside the tracks, not on them. Okay. Also, note, because I've read several stories about this recently. If you go for a run, don't run on the train tracks. People do this, and worse yet, they wear their headphones. I just don't see what part of that is a good decision. So you guys are all smarter than that. You're looking at me going, whatever. We'd never do that. People do it though. Okay, don't do that. All right. What change in frequency would you detect for the pitch of the whistle? So we're looking for F. Okay, if the speed of sound is 330 meters per second. All right. So they gave us V. So I'm looking for F. I don't even have to manipulate. All I have to be able to do is plug my numbers in and decide whether I'm adding or subtracting Vs. All right. Am I adding or subtracting? It says as it passes. So it was approaching. Okay, it was coming towards me. All right. So we're using add or subtract. subtract. Okay, so we just have to plug in our numbers then. 224, okay, 330 over 330 minus 30, okay, and that'll give us our proper frequency. So all right, so we would perceive a frequency of about 204 hertz, okay? And that would be noticeably different, okay? You would easily detect that change, right? Most people can detect a change in frequency of like within 2 hertz, okay, most of the time. If you have a really well-trained ear, probably even better than that. Okay, questions on how that one worked? Okay, so I want you guys to try, yeah, both of these. You guys can do both of these. There is a small trick in both of these. Please keep in mind that your speed needs to be in meters per second, okay? Okay, so we're crossing a crosswalk and an approaching driver blows their horn. Okay, the true frequency is 264 hertz, so that's F0. Okay, the car is approaching you at 60 kilometers per hour, so we need that in meters per second. Okay, so we're looking at 16.6 repeating. Okay, what is the apparent or Doppler frequency of the horn, assuming the speed of sound is 340 meters per second? So again, that doesn't require us to do any manipulation. We're just plugging in our numbers here. Are we using plus or minus? Minus, it's approaching. Okay, so we have 264 times 340 over 340 minus 16.6 repeating. Okay, and that'll give us our 278 hertz, which makes sense. We should hear a higher frequency of sound because the object is approaching us. Okay. Okay. Any questions on that one? Everybody's good there? All right. How are we doing on number 2? Some people are done 2. Okay, so we just need a little bit more time. Okay, so in number 2, we're told the airplane's approaching at a speed of 360 kilometers per hour, which means its speed in meters per second is 100 meters per second. Okay, if you measure the pitch of its approaching engines to be 512 hertz, so that's the frequency we hear. What must be the actual frequency of the sound, assuming that the speed of sound in air, that should be Vs, okay, is 345 meters per second. Okay, so we're looking for the original frequency this time. So F equals FO, V minus Vs, because it does say approaching in the question. All right, so if we're looking for FO, we just divide the entire bracket over to this side. Okay, and we've got what FO will come out to. Okay, so when we plug in our numbers, that'll be 512 divided by 345 over 345 minus 100. Okay. It's 245. Okay, so the actual frequency is quite a bit lower, as it should be. Okay, 364 hertz. Okay. Questions on that one? Okay, I would like you guys to do number 4. You don't have to do number 3, okay, but you do have to do number 4. Okay, so give that one a try. In number 4, okay, you are looking for speed of the source this time. All right, so number 4 is the tricky manipulation, right? We're solving for Vs in this one. So we have the frequency we hear equals the original frequency, okay, V over V, and are we using plus or minus here? We're using plus because the object is moving away, it's retreating, okay? All right, so we're trying to solve for Vs, so the first thing we want to do is divide both sides by FO. So we have F over FO equals V over V plus Vs. All right, as we said, if I want to solve for something, I need it on the top. So I'm going to flip both sides. All right, so I'm going to have FO over F equals V plus Vs over V. All right, at this point, I'm going to multiply both sides by V, and then I'm going to subtract this V over to this side. Okay, so I'm going to have FOV over F minus V equals the speed of the source. Okay, so when I plug in my numbers here, I'm going to have 500 times 350 over 475. Minus 350. All right, so it's moving at 18.4 meters per second. Okay, everybody all right with that one? That's the trickiest that you would probably be asked to solve. Last year on the unit exam, I had a question about a train. It was like that one. And I rather liked that question. Okay, so in your workbook package here, there's a few questions I want you to do. I think I put them in different color. We'll just call it